There's one more relationship between linear independence of vectors and span that is a really nice thing to know. And it has to do with adding one more vector to a linearly independent set. So let's suppose that we have a linearly independent set of vectors v1 through vk, and we have another vector v that is not in the span of our first vectors v1 through vk. So the question I want to ask is, if we add v to this set of vectors, is the resulting set linearly dependent or independent? Well, to answer this question, what we can do is just think about a linear dependence relationship. So write a linear dependence relationship 0, the 0 vector, equals a1 v1 plus dot 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 plus ak vk. And then we need one more term for v. So let's say a times v. All right. Now, of course, there always is a linear dependence relationship among these vectors. The only question is there a non-trivial linear dependence relationship? So the question is, could it be possible that any of these coefficients are non-zero? Well, let's check. So first, could A be non-zero? Well, if so, right, if A is non-zero, then let's move the term with v to the other side. That would give us minus AV equals A1 V1 plus dot 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 plus AK VK. But then we can divide both sides by minus A. That gives us V equals minus A1 over A V1 plus dot 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 plus minus, I guess this should be a minus 2, minus AK over A times VK. All right, and again, we can divide by A because A is not 0, right? We're assuming A is not 0. But this would mean, look, we've demonstrated that V is a linear combination of the VKs. So V is in the span of V1 through VK. But we assumed at the very beginning that that wasn't the case, right? So that's a contradiction. So actually, now we know that no, A can't be non-zero. A must be 0. Okay, so right, this coefficient, we know it has to be 0. So now that we know this coefficient is 0, we can actually rewrite this linear dependence relationship. So our linear dependence relationship becomes 0 equals A1 V1 plus dot 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 plus AK VK. And now I don't need to write the term for V because the coefficient on that term we now know is 0. Okay, so now we have this linear dependence relationship. But look, this is a linear dependence relationship only among the V's, only among the V sub i's. So V sub 1 up through V sub k, we assumed at the beginning that these are linearly independent. And that means that A sub 1 has to be 0 all the way up through A sub k has to be 0. So our linear dependence relationship at the very beginning, 0 equals A1 V1 plus dot 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 plus AK VK plus AV. Well, now we know all of these scalars are actually 0. So this linear dependence relationship is the trivial linear dependence relationship. So right at the beginning, we wrote down an arbitrary linear dependence relationship, and what we derived is that actually the one we wrote down is the trivial relationship. But that means that the trivial linear dependence relationship is the only linear dependence relationship, and this means that V1 through Vk together with V are linearly independent. This is really nice to know because often you'll want to know what happens to a collection of vectors if you add one more. And what this is saying is, right, if we have a collection of vectors, it gives us some span, right? If you take some vector not in this span, so like this vector maybe, the span of all three, well, these three together are linearly independent, right? If we started with two linearly independent vectors and we added a third not in the span of the first two, then all three together are linearly independent. But that means that the span of all three has to be bigger than the span of just the first two, right? If the collection of all three is linearly independent, then that means that there aren't any redundancies when you take span. So this tells us that, right, if you start with a linearly independent vectors and you add one more, you are really adding something new. You're making the span bigger.